Hey guys, welcome to the channel. So in today's video, we're going to be doing the PID part 2 video. So the long awaited, the much requested part 2 to the first video. If you haven't seen that first video, you might want to go check it out because we're going to be building on a lot of these concepts. Basically what we're going to be doing in this video is you guys are going to be seeing my screen. I'm Jonah, by the way. You're going to see my screen and I'm going to be live coding this simulation in Python for a PID controller. And then Luke here will be talking with me and we'll just kind of be talking back and forth and going over some of these concepts.
Yeah, so I'll be in the background discussing some questions that we've been asked on our Discord and also questions we've been DM'd on Instagram. We'll be kind of just working through those, discussing kind of a little bit like a podcast. And it's also a great time for me to mention that we do have a Discord, which you can join with a donation of any amount. It's a great little community of over 20 people now where we just talk about similar projects, really have a great time all around. Yeah, a lot of good people on there.
There's tons of really awesome people there, and like we're always online answering people's questions, talking to people, releasing some behind the scenes content, so should definitely check it out. Alrighty, so here we are. I'm just in a general text editor, so this is Sublime Text 3. You can use any text editor of your choice. You could use Notepad if you want. I don't know why you do that to yourself, but you can use Notepad. Any text editor, PyCharm, I know some people use, some people just develop in the Python IDE. But my poison of choice for text editors is going to be Sublime Text here. And so I've just gone ahead and created a Python file here, a .py, and I'm going to go ahead and import some things that I'm going to know I want. So what Turtle is what we're going to be using to deal with all of our graphical side of things. So we kind of want to do a nice visualization to go along with the simulation, because I think that, you know, you can write all the math and code you want. That's kind of easy to do. But to actually kind of understand how your system's responding, I think it's really useful to have some sort of visualization to go with that. And I think, Luke, you also agree that like the times we've actually taken the extra 5 minutes to develop a little visualization to go with some software, it's definitely helped us understand more. I think you'd probably agree, right?
Oh, absolutely. Yeah. Our first test with Spectre, we didn't have any sort of simulation that we'd done. It was all a lot of guesswork. And we'd done math, but no simulations. And it was tough to kind of understand what was going to happen in some of our tests.
I've just made some space here for some global parameters. And I think it'd be a good time to sort of describe what we're actually going to be trying to achieve here, and sort of lay out as well, just for myself, like where we want to go and how we want to go about coding this. So we're going over to the infamous Paint Time with Jonah.
Oh, yes.
So for those of you who don't know about Paint Time with Jonah, basically, right, the best idea, or the best way to get any idea across to anyone is obviously with MS Paint. I mean, how else are you going to describe complex number systems, complex control systems, complex portions of code without MS Paint? So Luke and I use this all the time.
Yeah, let me tell you, every single thing that we've designed for just about every rocket has involved a Paint Time with Jonah over Discord.
This is very true.
It is a key part to our development.
So what I'm kind of picturing, what we're going to want to do is we're going to have we're going to want sort of a screen here with Turtle, this rocket that'll start down here. Okay, so we'll say our rocket has a liquid engine that we can control the throttle on very easily to head right up to here and just beautifully hit our set point line or our target line, and when it does, we're super happy. So that'll be Luke. This is Luke when the rocket beautifully hits that set line.
Dude, you're so good at art.
You know,
makes it so easy
people kind of say I'm sort of like a Picasso of MS Paint. I was bang on. And we're going to figure out how big we want the window to be. I'm going to say 1280 by 900. So we have our main function there. And so this will just create a new sim function. And then what I'm going to do down here is just run main. PID controllers their kind of inherent limitation is that they deal best with a 1 degree of freedom problem. And so this is a very good example of solving a 1 degree of freedom problem. We have a throttleable rocket that we want to get to a certain altitude, and it's kind of similar to how you'd want to treat a thrust vector controlled rocket. It's a 1 degree of freedom problem that you're using 2 PID controllers for.
Yep.
Marker, and so this guy's just going to represent our goal that we want to get to, and it's just going to be a visual cue as to us getting there. This would be a good place to make set point a global variable, and we'll say, I don't know, sort of 1,000 is maybe a good height in pixels for our guy to go to. And I'll say 15 and set point. And so now when we build the simulation, he heats himself off the screen. Okay, there we go. Deleted some of the main stuff, and I'm just going to do sim.cycle. And so what I'm going to do here is I'm going to be creating a cycle function inside of this class, and it'll just go to self. Give myself some space here, and basically this is where we'll do our simulation cycles. And so I'm going to say while sim, and I'm going to sim.true here. So actually while self.sim. So basically what I'm going to do with this variable sim is we'll define some parameters that we want to keep the rocket within. So maybe we want the simulation to only last for 10 seconds. It's a pretty reasonable time length, and we want to keep the rocket on screen, because if the rocket heads anywhere off of screen, then we know we've done a bad job, so we'd want to end the simulation so that we can tweak our PID values. So that's all I'm doing here.
Yeah, so something we get asked a lot, especially on Instagram, is how do I get started with designing advanced model rockets with thrust vector control? Like, what resources do I have to begin to learn the skills I need to do this?
I think the best place to start, definitely, is to make sure you've actually flown traditional rockets.
Yeah. So I mean, just even getting a couple flights under your belt will give you an idea of like how these things fly, how these motors work. Because that's something important to know and understand the safety concerns behind that, and just really the basic physics behind model rocket flight.
Yeah, I mean, like, literally, you can pick up like a standard Estes kit for like dirt cheap, and like it doesn't take much to set up and fly. But what it'll do is it gets you a good understanding of the fundamentals, essentially, right? So you understand that, you know, you need to have your center of pressure below your center of gravity, and like you just get a good understanding of these general safety procedures that you need to follow to fly a normal model rocket safely. There's a few key takeaways that I think we've kind of gotten. And so one of the key ones is like, well, the first one is like, don't be afraid of starting, right?
Mm-hmm.
Like it seems like a daunting challenge, but like just break things down. Like that's the engineering approach, right? You look at a problem and you break it down into its constituent parts. You think, okay, what can I tackle? What can I tackle well? And, you know, what do I need to learn more about, right?
Yeah. Sure.
And so I've gone out and laid out the physics with these set gets. And so basically we have our second derivative, or our vertical velocity, or our vertical acceleration, sorry. And so that's going to be our gravity plus thrust divided by mass. So thrust is going to be our input. That's the thing that we've said we can control. So this will actually be what the PID controller is outputting. So the PID controller is going to give us a thrust, and that's actually what's going to impact our system. And then, of course, this second derivative is going to have its own derivative, which is going to be a dy, or a velocity. This is our vertical velocity. You can see here I set that to 0 initially. So I set that to 0 here. I also went and laid out some gravitational constants, a max thrust that we'll use later, and a mass of 1 kilogram. Because that's roughly sort of in the range of what actually a thrust vector control rocket would look like in mass. Oh, we're also going to want to create a rocket object. So what I'm going to do is I'm just going to say self dot rocket. We'll make it lowercase, or actually let's call it insight. If we can spell, let's call it insight equals rocket. So now what we can do is we can say inside the simulation self dot insight, and this is the annoying thing about Python, is that you have to write so many self dots, but hey yo. And then we do dot set ddy, bam, set underscore ddy with thrust. And here what I'll do is, for now, I'm just going to set thrust equal to 5 newtons. So we'll be putting this in, and this is just so we can test it. We'll do self dot set dy y. And what you could do is you could actually encapsulate all of these sets into their own cascading function. The reason that I've done all of these explicit sets and gets is, one, so that we can kind of very clearly see all of the steps that are going on, and also so that we can kind of easily get DDY or pull these states of the rocket very easily out of the code. But if you're doing this yourself, you might want to just kind of abstract all of this into a simple function where self DDY takes an input and then it cascades down and actually changes all of the other variables for us. But for this purpose, I'm just kind of sort of explicitly doing all of it so that we can see all of the physical steps our rocket will be taking. Come in here into my global parameters and do a time step. And I'm going to just set this to 0.005. What we'll do is we will do time dot for time step. And I'm also going to want to do else and elif. Sorry, I forget you can do elif in Python. Elif. And then what we'll do is we'll do self dot insight. Nope. Dot get y. And if this is greater than, say, 800, self dot false, and we're also going to want to say elif. Copy this guy, and I'm going to flip the sign, is less than negative 800, self dot sim equal false. We will be able to see if it is all working. And it is not, because I have a syntax error, unexpected indent on block. Always have to watch your indents because you don't have explicitly stated scopes. Another unexpected indent. And there is no shape in square addition. So we can try running that. And we see it. Initial X is not defined. Did I spell something wrong? Initial. Oh my gosh. I spelled it wrong here as well. Jeez, oh, I have stupid fingers. Oh, it's still an error? Name initial Y is not defined? Oh my gosh.
It's evil.
Dude, I'm totally gonna do a compilation of me spelling things wrong. There we go. Much better. Still very quick, but that's okay. I'm gonna make this 10. So you should hopefully see There goes the rocket. Beautiful, huh? So you can see him. He's going.
Looks great.
He goes to 0, 0 though. I don't like that. So what I'll do is I'll just change that to that. There we go. So now you can see we have a rocket and he's accelerating. So this right here is a perfect example of a system without control. And okay, so what I'm going to do is I'm going to make a class and I'm just going to call it PID. And inside, oops, sorry. Inside here, we're going to want to take in the classic. So obviously you have to do self, but then we're going to take in KP, KI, and KD, and a set point. Actually, to save confusion, I'll call it a target. So this is the target that we want to achieve. And I'm just going to write some boring code here. So Luke, maybe you want to answer another question?
Yeah. So another question from the Discord was, are the P term, the I term, and the D term all necessary for good control?
That's a good question. So essentially, it depends on what you're controlling, obviously, right? But we'll keep this in the context of thrust vector controlled rockets because that's why we're all here and they're super cool. You could probably get away without an integral term. So you could probably just do a PD controller on a thrust vector controlled rocket. The integral term, as mentioned in the last video, it just builds up over time. And so it essentially is going to look at, as the rocket flies, how far away and for how long are we away from our target. Now, a thrust vector controlled rocket only really has, we'll say, about 3 seconds of actually controlled flight, right? Because you can only gimbal the motor for about 3 seconds. And so you can kind of imagine that you're not really going to be building up a lot of integral error in this time, because there's only 3 seconds to build up integral error. So I imagine that you could probably get away without using an integral term. You could just look at the proportional and derivative and have a reasonably controlled rocket. But what that won't account for is things like misalignments in your thrust vector controlled mount. So say, we calibrate our thrust vector control mount, but it's never going to be quite perfect. And so this integral term is going to allow us to slowly correct over time back to an upright position. And it's also going to help minimize translational motion.
And the D term, right? That's going to be very important achieving quick control, right?
Yeah, because the derivative is looking at how things change over time. Mm-hmm. And with a system that's responding and moving as quickly as a rocket, is you want to be able to calculate and adjust more very quickly if you're about to overshoot your set point. And if you're about to, swing the rocket really hard, you want to be aware of that.
Mm-hmm. But then again, in a system like this, there's really no reason to leave one out. And so might as well include them.
Definitely want to include all of them. These are just regular E term. This is going to be our integral E term, and it's going to be our derivative term. And then we're also going to do self dot. So that's all good. There's one last thing we want to do for the derivative one, which is to do a self dot error last, so that we can actually do a comparison. And then what I'll do is set a actual compute, and this will take in self, and it'll take in the current value, position. So the first thing we're going to want to do is actually compute our error, and that is going to be equal to our current pause, or our target rather, minus our position. So that is all that our error is. What we'll do is we're going to do self dot integral error plus equals self dot error. So basically what we're saying here is we have our target subtract our position. So how far away are we from our target position? That's going to become our error. Our integral error is just going to be the sum of this over time. So if this is negative, then it's going to take away from our integral error. If this is positive, it's going to build up to our integral error. Then we want to look at the derivative term. And a derivative term, if you remember, is just going to be the change of something over time. So the derivative error is going to be equal to the current error minus divided by a time step. And the nice thing about defining constant time steps is that we can simply just define or divide. We don't actually need to compute this time step at all. We can simply take from our simulation parameters this time step to divide. Cool. And so now we have all of these. Oh, I've just realized I've made a mistake. I need to also multiply this guy by our time step, because obviously not only do we want to add the error, but we want it to be error with respect to time, right? What we want to do is set our last error to the actual error. And so what's going to happen is we're going to come through here, do all our computations, and at the end of doing these computations, we're just going to set the last error to what the error value is currently, so that when we come back through to do this calculation, this value, self.error, is going to be stored, or the current value for self.error will be stored in self.error last, so that we can actually calculate the change in this. And so the last step we're going to want to do is literally just this PID equation. So we're going to take our KP, multiply it by our error, our KD, multiply it by our derivative, and our inner KI, and multiply it by our integral. So we're going to do self dot equals. So we're going to take our self dot KP, so our proportional gain, and multiply it by self.error, our integral, so self.ki times our integral error and derivative error, and I'll keep the order the same. And bam, so there's our output. And now what I want to do is I want to check that the output isn't going to be unreasonable. And also, we want to return self dot. And so, actually what I can do is I'll go ahead and run this. Is our PID. That's a PID class. It does a simple PID controller. So what I'll go ahead and do is just add this into our simulation. Okay, so I've gone ahead and added it into our simulation. So here you can see I create a PID object inside our simulation. I just call it self.pid, and we initialize it here with our KP, KI, and KD. So I've made these gains a global parameter just so that we can change all of these things really easily at the top of the file. It keeps it nice and accessible for us. So we create a PID object inside of here, and during our loop, so while the simulation is true, we want our thrust value to be equal to the PID compute given the current Y value of our rocket or InSight. So you can see it takes in here on compute, it takes in a position, and we go through all those calculations that we know and love. So We then take that thrust, we input the thrust to the physics, get the actual response of the system, and then just check. And so if I go ahead and run this right now, you'll see we immediately have a thrust output of about 22,000 newtons. Now, that's a lot of newtons, and I don't think our rocket that weighs 1 kilogram is capable of producing 22,000 newtons of thrust. If it can, then, I mean, more power to it, but we're going to want to actually put in some checks in here to make sure that our output isn't going to be 22,000 newtons max thrust. Then we're just going to set it to max thrust. So this is what's called the saturation of your response. This is, we have to respond within something that's actually physically reasonable. And we also now want to check that if we've actually overshot, that we can't produce negative thrust, because obviously, like, we don't have a vacuum as our rocket engine, so it can't actually suck thrust in and pull the rocket down. So we want to say if the output is less than or equal to 0, and I'll change this to an LF, and that's because self.max thrust is not actually a thing. It's just max thrust. So now when we run it, you can see he's kind of trying his best. Oh, he's coming back up. It's not terrible. I mean, it's a pretty slow response, right? And for rockets, we kind of want things to respond pretty quickly and rapidly. So there you go, simulation ran out due to time. But what's really interesting is you can see here, we've actually limited our output. So it's always within the range that we've set it to. Now, such high gains, so our system isn't optimally tuned, because you can kind of imagine what you want the system to do is have a lot of thrust, and then slowly start to bring that thrust back right as we get really close, and then just hold a steady value of about, well, exactly 9.81. Cool. So you can now take a moment and celebrate, do a little dance, get the music going, because essentially what we've done is we've created a PID controller. I mean, this right here is a PID controller, and we've actually created a simulation for it. So, you know, pat yourselves on the back. I'll give you guys a high five. Just use this simulation as like a sandbox to play around and see how different values impact the system. And so, like, for example, one of the questions we answered earlier was, you know, do you need this integral gain? So we can take away this integral gain and just see how the system responds. Not very optimal. Do is I'm just going to add self dot, let's call it poses, which is just going to be an array. And what we're going to do is we're going to use this array, and you know, you may remember from basic computer science that an array is just a list of numbers. I mean, it can be a lot of things, but in this case, it's just going to be a list of numbers. And so what we're going to do is we're going to store our positions and our times. Okay, so now we have these, and hopefully when we graph it, so we should see a nice little sine wave, because right now we have steady oscillations, and bam, there we are. There's our nice graph. So cool, so now we're actually getting data back from our simulation. Alrighty, so we're on the home stretch now. We just need to figure out our gains. And so, you know, the ones that we had before were pretty reasonable, but there is a honest to goodness best set of gains that we can figure out. And so there's a few ways that we can do it, but the way that we're actually going to be going for is called the Ziegler-Nichols approach. And so that's what's called a heuristic method. So essentially it's not mathematically the best output or the best set of gains, but it's a pretty dang good set of gains that we can figure out relatively easy without having to do any crazy math where we can simply just observe the system, which is nice that we can do because we have a nice simple simulation here. So we can observe the system, get a little bit of information about it, and get a response that's going to be very acceptable. And so we're just going to quickly run through that process right now. So I've got the Wikipedia page for the Ziegler-Nichols method pulled up right here. So here you can see, yep, so they describe a heuristic method for tuning a PID controller. So yeah, our boy John G. Ziegler and Nathaniel B. Nichols, very smart people, they figured out this relationship. Because essentially, what you care about most with a PID controller is the relationship between the three gains, the KP, the KI, and KD, because how they play off of each other, or the ratio of them, is very important. So essentially, we have 0.6 KU, where KU is our ultimate gain. That sounds really intense, but in actuality, all it really is the largest proportional gain we can have where we still have steady oscillation. I've also gone ahead and changed our time step to be milliseconds because this will make calculating our period really easy. So I'm already gonna, we'll just type 0.2 and see how the system responds. Cool, so you can see those are pretty steady oscillations. There's a tiny bit of fluctuation in there, but for the most part, the peaks and troughs are relatively comparable. So we're gonna keep going up. I'll bump it up to like 0.5. Essentially, we're just going to keep pushing it until we break it. And that's what's so nice about a simulation is it doesn't rely on a physical rocket to get broken. You can just break your simulation. So these are still pretty steady. So I'm going to go ahead and bump them a little bit more, so 0.7. And let's see how this responds. So visually, it looks like there's definitely some fluctuation in here. And yes, so we're definitely starting to narrow back in. So these are not steady oscillations. So we're going to want to dial this back a little bit. Let's try 0.6, right between 0.5 and 0.7, and see how this looks. It's pretty close. I'm going to say that it's steady enough. So now what we're going to do is we're going to want to figure out our period. And this is why we imported matplotlib all along. It's got this really nice functionality where we can just zoom into a rectangle. So I'm just going to take 2 peaks there, and if you remember from high school math, or probably actually no, way before high school math, the period is just the distance between 2 troughs or 2 zeros. I'm going to do these 2 peaks because that's nice and easy to identify. So you can see the peak point right here, and if we look on the bottom right down here, you'll see that we have an x value of about 9. I'm going to call it 9 to keep it simple, and this peak is about 26, 27, so 27 minus 9, and that'll give us 18. And I'm going to go ahead and close the simulation. Cool. So 0.6 is our KU, so I'm just going to make a note of that. So our maximum response. And if we come over here back to the Wikipedia page, we can see it's 0.6 times our KU. So 6 times 6 is 36. So our KP is going to be 0.36. Sweet. And I'll also make a note of that period we found. So TU is equal to 19, I think I said 18 milliseconds. And your units here are very important because we are actually going to want it in our standard kilograms, newtons, and seconds units. So we'll want to actually convert that back to seconds. But we have our KP, we're going to want to figure out our KI, we're also going to want to figure out our KD. And I have these commented just now so I can keep a note of them, and then we'll comment them back in when we're ready. Cool, so I have this article here, and I've also booted up a small Python IDE terminal here, just so we can quickly run these calculations. So our KI is defined as 1.2 times our KU, which is 0.6, divided by our TU, which we defined as 18 milliseconds. So we're going to want to divide this by 1,000 to actually get our TU in seconds. It's cool. So 40. So I'm going to keep a note of that. So I'll copy and paste that over here. So our KI is 40. It seems quite big, but it kind of makes sense, right? Because we don't want to be away from our set point for a very long time in this case. We come back over here, and I'm going to build up in this Python terminal again. And we have 3 times our KU, so 0.6, times our TU, which which we defined as 18 divided by 1,000. And all of this, so I'll put one more set of parentheses, all of it is going to be divided by a value of 40. And there's a syntax error there. There's multiple syntax errors there. Cool. So that is our value for our derivative gain. So you can see that the relationship between these is very important. And what we'll do is I'm going to comment these out, and these will be our new gains now. This should be a very acceptable response from the rocket. It should be very snappy, and it should get to our set point very quickly, because we've done this heuristic approach to get some pretty good gains. And there you can see that is a beautiful response. You should see on the graph, it should be perfect. Look at that. That is definitely the exact response we want. This is the position over time, remember? So we start all the way down here at negative 100. We boost up really quickly, we overshoot a tiny bit, and we settle back down pretty nicely. So there you can see the Cyclo-Nichols approach in action, working pretty dang well.
All right, I'm back. How's the sim looking?
It's looking good. So I added in
Sweet.
I went through the Cyclo-Nichols approach. So that
awesome.
It's now actually all tuned. So do you want to see the tuned response?
Yeah, I'd love to. Oh, dude, that looks so much better.
Mm-hmm.
That's
You
perfect.
should see on the graph too. Yeah, there we go.
Oh, wow. Awesome.
So yeah, it's real smooth. Tiny bit of overshoot, and then just comes back and settles in like real nice.
Yeah,
So,
for sure.
I mean, yeah, we could even go in and we could change the set point, and just bump it up to like 40 and take a look.
Looks great.
Still super nice.
Dang, nice work.
Yeah. So there we go. That is it. After what? How long was that?
Dude, I think we're here for, what does Discord say?
Three
It's
and a half
almost 4
hours?
now.
4 hours? Jeez. Yeah. Well, there we go. I mean, we answered some good
Worth it.
questions, and yeah. Now we have a full simulation. So
Absolutely.
yeah, I'll be putting the GitHub link to this in the description for everyone. So if you want to go check it out, play around with it, please do. If you do something cool with it, like maybe you make one that flies up to the altitude and then actually does like quote unquote propulsive landing or something, send it to us. Like, we'd love to see it. Tweet it, make a commit on the GitHub, whatever you want to do. We'd love to see it. So yeah.
Yeah, we've also been working very hard on Insight. That has been a super long project, but we're almost to the point where we're ready to do a hold down test. We're planning on doing that within the next couple of weeks, hopefully. So be on the lookout for a new video. You guys should be very excited to see that new vehicle. It's going to be cool.
It's going to be, yeah. Like, I alluded to it in the last control video, that it will be unlike anything anyone's ever seen. And we still stand by that. It is definitely, from an engineering standpoint, the best thing that we've created on the channel by far.
For sure. Mm-hmm.
Like, the amount of time and effort we've actually put into like front loading the work and looking into each part and doing things properly is awesome. There's gonna be so many cool features on it. And yeah,
and I think all the work we've done is going to pay off. We're going to see some good results with the tests we're going to be doing on this thing.
Yeah, hopefully, and so hopefully it'll make for exciting content for you guys as well.
Yeah. So as always, remember to follow us on Instagram, on Twitter, and subscribe and like this video on YouTube.
At Orion
Aerospace.
Aerospace. That's it. It's
On
at
all
Orion
platforms.
Aerospace, all platforms, except for Twitter, which is at Aerospace Orion, and the Gmail, which is orionaerospace.liftoff@gmail.com. So, but yeah, with that, hopefully this wasn't too boring.
Yeah. Thanks for sticking around. You guys did better than I did.
Yeah, this is true.
I was gone for half the time.
You got hungry.
So.
To be fair, I got hungry too. I just paused the stream and no one actually will know.
Well, you're a trooper.
But I'm a trooper. So thank you guys again, as always. And we will catch you in the next one, which should hopefully be an exciting video. Rockets out.